All right, so the definition of work is the amount of energy you expend to do work, or to the amount of energy you expend to move an object, to displace an object. And energy is the ability to do work. So just right there from the definitions, you can see that the two are actually the same thing, if you will, somewhat opposites, but still the same. Work is energy and energy is work, thus work-energy theorem. What that means is, if I am going to do work, if I'm doing work or an object's doing work, it needs to lose energy, thus the negative sign there. It loses energy. Lots of times that'll come in the form of potential energy lost, although there are some situations where that should be negative kinetic energy. Likewise, if work is done on an object, if work is done on the object, then you are going to gain energy there. So if you do work, you lose energy. If you have work done on you, you are gaining energy. Now, I should point out, whenever work is done on an object, that's actually considered negative work. Instead of the object doing work, work is done on it. So really, these two equations are the same thing, but the concept is what I need you to get here. The concept of work and energy are the same thing. Whenever you do work, you're losing energy. Whenever work is done on you, you're gaining energy. And then you're going to use somewhat kind of logic to say, okay, this work is being done, and that work that's being done is going into what form of energy, and then continuing to solve from there. So let me work a couple of problems for you to try to help clear that up. All right, so here's a rocket problem, similar to ones that we have done in the past. A rocket its engine can apply a force of a little over 1 million newtons to lift this huge 42,000 kilogram rocket skyward. The engine, how long is the engine going to end up having to burn? How far must the engine end up having to burn to get the rocket to outer space 100 kilometers away, kind of being that verge there. So we'll say once it reaches 100 kilometers, it's going to establish an orbit at that point in time. Now, if we were going to work this without energy, we would just simply say, all right, the rocket is going to accelerate upwards. Let's neglect it going at an angle. Let's go straight up. So I would need to do Newton's second law to find the acceleration. Then once I have an acceleration, I have a two-part kinematic problem. I have how far it's going to go in the acceleration piece, right? And then up here is my 100 kilometers. So I'm actually going to kind of work backwards through this whole thing to calculate what I need. And that's going to get really long and hairy very fast trying to attack this with Newton's second law and with kinematics. Plus, that's not taking into account that if a rocket is going to establish an orbit, it actually needs to go at an angle going through the atmosphere, and that angle needs to gradually change. And whenever you're dealing with Newton's second law, that becomes a lot tougher there. So neglecting air friction, using work-energy theorem makes this a lot easier, because work and energy are scalars. You don't have to deal with the angle. Plus, you don't have to deal with any of the multi-step things. Work is the same thing as energy. So the work the rocket's engines do, and I'm just going to use W for that, or maybe I'll use WE, is going to equal how much potential energy, PE, the rocket gains. So the work the engines do then is translated into potential energy of the rocket. So this is going to be force that the engine exerts times how far, delta Y, let's say, the engine ends up having to push, equals potential energy of the rocket, mgh and h final, what we're trying to get up to. Now, if the rocket was starting out at some initial, then we would need a mghi, because technically this is going to be change in potential energy here, starting from what and going up to what, but our initial is going to be 0. So here I'll even kind of write this in really fast and erase it, mghi, and the initial height is 0. So we can just completely get rid of that part there, because we're going up to some final height. Now let me also point out, these two numbers are different. The final height is going to be my 100 kilometers. That's how high I want the rocket to get up to. But the rocket's engines don't have to burn for 100 kilometers necessarily, because the rocket's engines can burn for some shorter distance, build up speed and the acceleration portion, and then turn off. run out of fuel, which is kind of nice because then you don't have to pack too much fuel into the rocket. It's a little bit more efficient that way. And then it can use its inertia, right, and continue to coast upwards, losing speed as it goes, but eventually get up there. Now, under this circumstance, I'm calculating that it would have zero velocity once it reached that point. So zero velocity in the y-axis right now once it reaches that 100 kilometers. So what is the minimum distance, delta y, this rocket is going to have to burn if it can provide an average of just over 1 million newtons of force. So now let's start plugging in everything and we'll have what we need. This is going to be 1,050,000 newtons of average force. And I should say a rocket doesn't actually burn with a consistent force. It is constantly changing as the rocket loses mass due to the fuel being spent, burned, and shot out of the back. 9.81 for gravity on average, which, by the way, would also be changing as the rocket got up to a height, but never mind that. And 100 times kilo means times 10 to the third, and I'm not worrying about making sure that's in proper notation right there because it doesn't matter. So that's going to mean delta y is 42,000 times 9.81 times 100 times 10 to the third. Remember, it's not that big of a deal. Kilo means times 10 to the third. Just replace for the sake of time. Your calculator takes care of it. Just make sure that you're reporting things in correct notation at the very end here. Divided by the average force, and I get my delta y. And I come out with 39,240 meters, or if in correct sig figs, and I'm going to convert to kilometers here, 39 kilometers is how far the engine would burn if it's able to exert just over 1 million newtons of force there, and then it could coast the rest of the way. So it actually is burning even less time than, or a shorter distance, I should say, than the rest of the way up than the coasting distance. Here's another situation where conservation of energy and using work energy theorem is a lot easier than going through Newton's second law and possibly here and then doubling into kinematics, being able to solve straight through with it. I have a ball at the top of a hill that's 29 meters long and 12 meters high. Now, they might have given you the angle here and you had to solve for one of those. Not a problem. I'm told friction exerts an average force of 0.75 newtons, so they actually tell me what the force of friction is. And I want to know how fast is the ball going to be going at the very bottom of the hill. Now, kind of a note, if they give you the coefficient of friction, you have to go through that. Then it's kind of whichever way you'd like to solve it, energy or Newton's second law. It's about the same length of problem then. But if they give you the force of friction, much easier to go through conservation of energy. My personal opinion, it's even easier to go this way if you know the coefficient. So what I can say here is from conservation of energy, at the very beginning, I'm starting out with all potential energy. So at the very top of the hill, the ball starts out with all potential energy. And now, where does that energy go? Well, the energy, by the time it gets to the bottom of the hill, is converted into two places. It's converted into kinetic energy. There's no potential energy left. But it's also converted into work done by friction. Friction steals some of that energy. So all the potential energy initial goes into the work done by friction and the kinetic energy at the bottom. Okay, so final kinetic energy, and this is standing for work done by friction there. All right, so let's break each of these down. This is mghi equals 1/2 mv final velocity squared plus work is going to work done by friction is the force of friction times the length of the entire hill there. Well, now I pretty much know everything. I just need to plug in all of my numbers. And I end up with a final velocity of 12 meters per second here. After I work everything all the way down. Notice friction here, the work done by friction, so some of your potential energy goes into work done by friction, right? It ends up stealing 21.75, almost 22 joules of the just under 60 joules that there was in the beginning. So it steals about a third of the total energy that was there in the very beginning, leaving you with just under 40 joules of energy that is left to go into the final velocity at the bottom of the hill. And going about it this way actually is a lot easier, at least most of the time, than having to go through the entire Newton's second law problem and then dealing with the hypotenuse of the hill, right, or the length of the hill here with a kinematic problem.